And 3, 2, 1, we're live.
Good evening, everyone. Welcome to Amateur Astronomers Incorporated, also known as AAI, for our weekly Fridays at Home presentations. AAI makes its home at William Miller Sperry Observatory on the campus of Union County College in Cranford, New Jersey. Since the observatory is closed at this time, we are holding our weekly presentations online. Our presenter this evening is AAI member Steve Lowe. The title of his presentation is Spectroscopy with a C8 Celestron HD using the ALPY 600. So Steve, please begin.
Hi, thanks Mary. Tonight I'd like to present you with spectroscopy and what I've been trying to do and learn about spectroscopy. But before we get started, I'd like to introduce you to a couple of gentlemen long before Elon Musk, in fact, even before NASA. These two gentlemen almost weekly came up with new inventions. Very few were successful. In fact, I don't think any of them were successful. But they had a lot of forward thinking. And I'd like to introduce you to these two gentlemen that you may know, Ralph Kramden and Ed Norton. So look at the picture carefully. Obviously, Ed Norton's wearing the space helmet, and Ralph is a little surprised. But if you look at the picture carefully, see if you can find a piece of equipment that Ed has, and we'll talk about it later. And you never saw this piece by Elon Musk or NASA. So let's get started about spectroscopy. So spectroscopy is the analysis of the interaction between matter and any portion of the electromagnetic spectrum. It is such a powerful tool that most of what we know in astronomy is a result of spectroscopy. And that will probably be true for many years going forward. So what I did here was list a few missions, and just a few, that are searching the electromagnetic spectrum. As you can see, we have the HESS, the SWIFT, searching for gamma rays, New Star, Sandra for X-rays, New Horizons, which I'm sure everybody's aware of, for ultraviolet, the Kepler, the Hubble, the Kelk, the SALT for visible, the Spitzer, Herschel, Sophia for infrared, the Planck and the Karma for microwave, Green Bank and VLA for radio, and the Spirit and Opportunity, and again the New Horizons for infrared, as well as some of our, in fact, our first two real missions, Voyager 1 and 2, searching the ultraviolet. One of these you can actually visit, and it's Green Bank, which is in West Virginia. And here are 6 of the eminent scientists at Green Bank. Most of you know them. But in the background there on the left side, they have a small museum with a small auditorium, and they give presentations, science presentations. So inside, here's a picture of Joe and I taking a picture of ourselves by an image which is in the infrared. And this slide shows you the valley. This is actually a beautiful area, a beautiful drive. And there on the background is the big telescope, on this site, which is quite large, there are 8 telescopes. This one is the largest. And in fact that you can see at the title, this is the largest movable object on land. It was measured, I believe, at 485 feet, which is almost a 45-story building. And we were lucky enough that when we got there, we did get to see it actually rotate. Spectroscopy is done at all wavelengths of the electromagnetic spectrum. In the visible spectrum, light can be dispersed by either a prism or a grating. The visible wavelengths of the electromagnetic spectrum are 3,600 to 7,600 angstroms, or if you take a 0 away, 360 to 760 nanometers. So first, this is my home-built observatory. It measures 6 feet by 8 feet, and the walls are about 5 feet. And when I designed it, I made the roof, or the peak of the roof, and I hope everybody can see my cursor, a little higher for 2 purposes. Number one is to shed the snow during winter, and allow me also to put in a larger telescope. So the way I constructed it, I could put in a 14-inch Celestron. And you can sit 2 people in it, but right now it's just set up for 1 person to sit in. In this slide, to give you an idea of the equipment I chose and some of the reasons why I chose it. This is the Celestron HD model. And the purpose of choosing this is that you can lock down the mirrors with these 2 knobs. In the background, you can barely see it. There's a 3rd knob for focusing. So on the back of the telescope, I attached a focal reducer, and that actually sits inside an electric focuser. So the purpose here is when I do focus with the telescope knobs, I get a very, very basic focus, and then I lock down my mirrors so that when I'm moving the telescope, there won't be any mirror flop. Then I can control the focus through either it has knobs on it where I can do it manually. It also has a paddle, which I can do it electrically. And better yet, I have software on the computer that can control the focusing. And that's actually the best way to do it, because that software will tell you exactly how far you've moved the telescope and gives you a readout so that you can carefully adjust it as temperature changes through the seasons. And you can always go back to a setting whenever you want. The device behind the focuser, this is actually the spectroscope made by ALPY, or made by Chiliac. It's called the ALPY, and this is really a low-level or low-resolution spectroscope. And on top here, the round disc-looking shape is a guide camera, and in the back I have another camera which actually captures the images. So here is a pictorial of the ALPY, the spectroscope, and how it works. What advantage this spectroscope has is it has a slit. So what a slit does for a spectroscope, it provides two things. It helps to block out outside light. So you can put that slit, which happens to be 23 microns wide. So to put that in perspective, that's about half the thickness of a hair on your head. And the slit is about 3 millimeters long. So when the light goes through it, it diffracts. A collimator directs that light at the actual device, the dispersion device, and in the ALPY, we call it a grism. And it's a grism because it's a combination of two items, two pieces of glass. One is a transmission grating, and the other is a prism. Once it goes through that, another lens will focus each frequency at the focal plane, which would be the actual camera. So here's an image, just to give you an idea of what I see through the guide camera is the actual slit. And remember, this is 3 millimeters long and 23 microns wide. And here I'm focusing just above the trapezium in the Orion Nebula. So when I go after an image, one of the aspects of doing spectroscopy is to be consistent in the sense that you want to get that slit in the same position. In fact, if you can, on the same pixels for each image. And I can do that simply because the software allows me. So when I take a picture in SkyX Pro, the image I see will tell me if I point my, if everybody can see that, I can point to any spot, and in the lower left-hand corner, the software will tell me exactly what pixel I'm on. So here we have a pictorial image from NASA of the different levels of our atmosphere, the troposphere, the stratosphere, the mesosphere, thermosphere. And and across the top, we have the different types of electromagnetic spectrum and what actually passes through our atmosphere. And as you can see, in the middle, we have visible. And obviously, that passes through our atmosphere, but very little of the ultraviolet and a little bit of the near infrared. And this little model of an airplane represents Sophia, which is actually a flying telescope. And they fly about 45,000 feet, so they can gather a lot more infrared data during a night. On this slide, what I'm showing you here is two things. Number one, on the left hand, the vertical or the Y column, we see each type of star that's currently labeled. O-type stars, B-type, A-type, F, G, and our sun is a G, K, M, down to M2. And across the top, we have a list of elements, and across the bottom, we have a list of elements. So what we see here are what we expect to see, and these types, what they do is actually represent the temperature of the star. So the O star is the hottest, and what we can see here is we can see hydrogen alpha, and it keeps being pretty strong. It shows pretty strong, and then as the temperatures cool, the cooler stars, we can barely see it. We can also see that with the different parts of the Balmer series of hydrogen, hydrogen beta, and such down the line, including helium. At the bottom, we see the cooler stars and what elements we expect to see in these cooler temperatures. And in here, you see a lot of TiO, titanium oxide. So this is actually, it's cool enough as Betelgeuse to show molecular activity. In this slide, what I try to show you is the temperature of the photosphere. So when we look at the sun and we measure the sun, most of that light is coming from the photosphere. And this graph tries to depict what elements you would expect to see at what temperatures. So at the top, we obviously have the temperatures, and the bottom, again, we have the different star types going across from the very hot to the cool ones. And this, especially for a beginner, is very helpful, because if you're finding hydrogen very strong and you think it's an M star, you're wrong. So this assists, especially again, beginners, to identify the type of star they're looking at if they're not sure what to expect once they see their spectrum. So these are some of the projects, or the main projects, that I've been trying to do throughout the year. And my size, the size of the telescope, and also considering the atmosphere conditions in New Jersey, I'm probably limited to a magnitude of 5 or 6. I can try to get to a dimmer star or object, but I tend to gather a lot of ambient light, which can really overshadow the actual spectrum. So throughout the year, what I try to do are the spectrum and the photometry of the Cepheid variables V42 and V84 in the globular cluster M5. So this is time of year to see that. I have a list of supernova candidates throughout the season that I can see. I also have a list of Wolf-Rayet stars. And usually I go after Wolf-Rayet because some of the Wolf-Rayet stars are candidates for supernova explosions. I also go after star-forming regions, quasars, and a study that actually was started by Dr. Mary Lou West are the variable ROAP stars. So that's an A star with peculiar elements showing in the spectrum. So here's an image that I took with a DSLR, and you can do spectroscopy with a DSLR, but generally it is more precise using a mono CCD. But in this image I pointed out, and you can clearly see them, are these two Cepheid variables, V84 and V42. So what I have to do is, when I look at this object, I line up that slit so the center of that slit is directly over the star without including any other stars. So for V42, that's possible. because the way the focuser is designed and the spectroscope, they're attached to each other. So I can maintain the exact position of the spectroscope, but rotate the whole focuser. So the focus isn't disrupted. This picture was actually taken with a DSLR on the 24-inch at Sperry. So here is the next part of this presentation is to kind of show you what to expect when you find a spectrum, what they should look like, and what I'm actually trying to improve to get a better spectrum. So here we actually see a what they call a 2D image. So this is the actual image the camera takes. And you can see it's a nice straight long line. And in this, we can see clearly some dark spots or lines, and these are absorption lines. So the objective, especially for a beginner, Vega is very important. And it's important for a couple of reasons. One, it's very bright, very easy to find, and you really don't even need to have a mount. Because it's so bright, a camera can gather enough light in less than a second or a couple of seconds to get a good spectrum. This is also, and you'll see in the next image, this is what we call a 1D image. So this is the image brought into the software, and this software is called RSpec. And on the left side is the actual 2D image and what it looks like. And these horizontal lines around it are part of the software that permits you to block out any excess light that you don't want to show on the right side. So on the right side, and if you notice, it says it's in pixels. So this is a non-calibrated image, but it's still a 2D image. And at the bottom of it is a synthesis of this image here. And the upper image is really called a continuum. So the continuum is this bottom part and this curved area above the base or the horizontal. And in this continuum, you can see these absorption lines, very strong. And at the bottom, you can see the synthesis of these actual absorption lines. So the next process would be in this is to actually go through a calibration process. And in that process, you would identify what each one of these lines, what frequency they represent. So part of the learning curve is to know the basic stars like Vega, which is an A star, and understand and recognize what each one of these absorption lines, the name and the frequency. So here is another absorption line 2D image, but now this is Betelgeuse. Again, this has its own particular look. It doesn't look like, even though you can see the absorption lines, it appears different than the A star or Vega star. And the reason for that is we're gathering a different temperature, different frequencies. With this, basically, the range of frequencies is the same. But because of the temperature, we'll see absorption lines in different places. So here is Betelgeuse. Now we're back to the 1D. And this looks a little different than the AOV or Vega spectrum for a couple of reasons. As I said earlier, the Vega image was in pixels. It was not calibrated. In this image, we're looking at Betelgeuse, and the actual 2D image has been calibrated. It has also been adjusted for instrument response, and a third process, it's been normalized. So basically, what I mean by normalized, I've flattened out that continuum. It's still a continuum, but now it's flattened out. And as you can see, it looks quite a bit different. There's no definite lines, clear lines as in Vega. We still can see some hydrogen alpha, but primarily, as we saw in the pictorial, it's a cooler star, so we see a lot of titanium oxide. And the reason we see two lines in each place is the blue lines, the vertical blue lines, are lines that our spec showed as the titanium oxide. And the black lines, vertical lines, are lines I have identified from another study that Dr. Mary Lou West sent to me. And I put them in place just to see where they would show up. And this study was done recently concerning the eruptions that Betelgeuse has been showing. So part of the my studies and what I'm looking for is these objects that I'm after. The giants of this field really have done their the prep for any following professionals and amateurs like myself. So what I'm looking for is, once I take a spectrum, I do try to match it with a professional looking spectrum. And I do that to make sure that I'm performing and recording the spectrum correctly. And what I'm after is, I'm looking for any changes that may erupt or occur in the spectrum. So here is an emission line spectrum, and right away you can see a difference between this and Betelgeuse and Vega. So what we get, a nice straight line. Again, as I'm trying to improve, I try to make this line thinner. And because this is an emission object, we see these bright spots. And these are emission lines that will show up in the spectrum. So what presents or what causes the emission lines is the actual star, the temperature, and what's occurring in this star. So Wolf-Rayet stars are very large, very hot, and they're giving off an enormous amount of energy and material, which causes these emission lines. So here is the 1D spectrum. Now this has been calibrated, and as you can see, the synthesis of the actual spectrum, the continuum at the top, synthesized below, and you can see the bright lines matching up or lining up with these emission lines. And on the left here, I put up a list from RSpec of the elements that I expect to see. So Wolf-Rayet stars come in three categories. WN, which would be nitrogen. WR, which is very rare, would be oxygen, but very rare. And the third type is the carbon, WC. So here we can see this Wolf-Rayet 136 is a WN, and it's in the Crescent Nebula. And the Crescent Nebula, the emission is an emission nebula, and the main source of that is this Wolf-Rayet star. So here is a P Cygni, a 2D image. This is also a star that's giving emission lines. And you can see, again, different temperature. The Wolf-Rayet stars can be very hot. The P Cygnis are a little cooler, somewhere in the range of 18,000 degrees Kelvin. And here the line looks different, a little different than the Wolf-Rayet, but you can still see the bright spots, which are part of the emission lines. You can also see down here some absorption lines, which actually may be part of our own atmosphere. And if it's clear enough for you, you can see some vertical lines here in the background. So in this case, this image was taking a little bit longer to gather the light. And while you're doing that, you do pick up some ambient light. In this case, I didn't put it through any software to eliminate it in RSpec. So here is the 1D image of P Cygni. And the nice thing about here, again, the synthesis of this continuum, we can see the bright emission lines down as low as 4,000 angstroms up to the 65, 62, which is hydrogen alpha. But clearly these line up very nicely with the emission lines, all the Balmer series of hydrogen alpha. P Cygni is also a luminous blue variable. And the interesting thing about this star, or this type of star, is that it, again, as the Wolf-Rayet, it is blowing off huge amounts of material, which creates, in this particular star, a very unusual situation. So here is the prior 1D image, and I zoomed in on hydrogen alpha. So you can see this broad line showing the hydrogen alpha, and right next to it is an absorption line of hydrogen alpha. So in one image here, we have an emission line of hydrogen alpha and an absorption line of hydrogen alpha. And if we know the difference between number of angstroms between the absorption line and the regular emission line and where we expect it to be, we can actually calculate the speed at which these gases are being blown off. So part of my projects were looking for, and I added this on late in the last year, are star forming regions. So, and I showed you an image of what the guide camera would look like with a slit. And this is M42, fairly close to the trapezium. and this is a 2D image. And note the difference. These emission lines, these vertical lines, are spread out simply because this is not a point source such as a star. Since it's a nebula, the light is spread out, and this is the way the image is captured. So in the 1D image, again, we have the synthesis. Looks very much like P Cygni here, or the Wolf-Rayet, as far as you can clearly see the emission lines that are synthesized down here. And they're lining up nicely with the elements, some of the elements on the left side pointed out here. And if you look here on the left side, you can see how I place the horizontal lines to capture as much of the actual lines from the nebula. And I also can see some shady areas here, and that's some of the ambient light. And these are some of the resources that I use. There are hundreds of resources. These are some of my favorites. There's an enormous amount of reading, but I've enjoyed part of this little journey is not only discovery, but just learning for the sake of learning. And I want to thank everybody for listening. And any questions, I'll be glad to hopefully answer.
Okay, thank you, Steve. So join us every Friday night at 8 o'clock online. Our presentation next week is orbital traffic congestion and space junk detours. So thank you for joining us tonight and wishing you clear skies.